Hi, thanks for joining me. In today's video, I'm going to be proving that e to the m is irrational for any positive integer m. So I've already made a video in which I proved that just e is irrational, so I'll leave a link for that in the description below. But today I'm going to be proving a more general result, that is e to the m is irrational for any positive integer m. Let's get stuck into the proof. Okay, so we start this proof by introducing a family of functions fn of x. So each fn is from the closed bounded interval 0, 1 to the reals, and it's defined as follows. So fn of x is equal to 1 over n factorial times x to the n times 1 minus x all raised to the n. Okay, and I have two claims about fn. First one is that fn of x is non-negative, but it's bounded above by 1 over n factorial, and that's for each x in this range here. Okay, and the second claim is that the jth derivative of fn and the jth derivative of fn at 0 and the jth derivative of fn at 1 are always going to be integers, and that's regardless of what natural number j we choose. So no matter which positive integer j we choose, these guys here are always going to be integers. So let's kind of just talk through these claims and kind of talk through the proofs as opposed to writing them down. This one's kind of obvious. Firstly, to see non-negativity, well, clearly x is at least 0, so x to the n is going to be at least 0, and then 1 minus x to the n, well, because x is at most 1, we have that 1 minus x is at least 0, so this guy here is at least 0, so at least 0, at least 0, and at least 0, so you're multiplying three non-negative terms, of course that's non-negative, okay, and to show that it's bounded above by 1 over n factorial, well, because x is at most 1, x to the n is at most 1, and because x is at least 0, then 1 minus x is at most 1, so these guys are at most 1 to the n times 1 to the n, which is 1. So fn of x is at most 1 over n factorial. And you can probably make this upper bound a bit better as well, using perhaps some calculus. But that's not necessary for this video. We just need this upper bound here. Okay, and the second claim, the jth derivatives of fn at 0 and 1 are always integers. This is a little bit more difficult to see, but hopefully it's not too difficult. Firstly, have a look at this guy here. It's just a polynomial of degree 2n. So certainly when you differentiate it at least 2n plus 1 times, you're just going to be left with the constant 0 function. So of course, these guys are both going to be 0, which is an integer. So you only really need to focus on the case when j is less than or equal to 2n. And you can see sort of for the first n minus 1 derivatives, if you just focus on this guy here, the first n minus 1 derivatives of fn, when you plug in x equals 0, there's always going to be a leading x term out front. So that's always going to give you a 0. So you really need to focus on j being between n and 2n inclusive. And then for that, all you have is kind of this guy here, multiplied by an n factorial and divided by n factorial. I'll leave all the details for you if you want to go through it. But yeah, hopefully it's not too difficult to see that these guys are always going to be integers. But if you don't believe me, just go through and sort of go case by case when when j is at most n minus 1, when j is at least 2n plus 1 I dealt with already, so you're just left with the case when j is between n and 2n minus 1. But I'll leave that as an exercise for you. Anyway, let me clean up the whiteboard and we'll continue. Okay, so now what we're going to do is introduce a new family of functions, capital Fn, from the bounded closed interval 0, 1 to the reals, and each fn of x is defined to be equal to the sum from I equals 0 to 2n of minus m to the power of 2n minus I multiplied by the ith derivative of f of x. So it's kind of a weirdly defined function. Oh, this is supposed to be fn of x. Okay, it's a bit of a weirdly defined function, but we'll see why it's important in just a second, and it's kind of why we're constructing it. Let's consider the derivative of this function. So f prime of nx. And of course, because we can differentiate each term because we're just summing up a bunch of terms, all you have to do is differentiate this guy here. So it's a sum from I equals 0 to 2n of minus m to the 2n minus I times the I plus 1th derivative of x. Okay, like so. But of course, we know that when we plug in I equals 2n, here we're going to have the 2n plus 1th derivative of fn, but if you remember, fn is just a polynomial of degree 2n, so if you differentiate it 2n plus 1 times, you're going to make that final term vanish. Okay, so we only really need to sum to 2n minus 1. Okay, now what we want to do is just essentially do a little shift of the terms. Okay, so essentially bring up the I, so we can get this thing here in terms of I as opposed to I plus 1. So what we're going to do is the sort of substitution j equals I plus 1. So this summation now becomes the sum from j equals, well, when I is 0, j is going to become 1. And when I is 2n minus 1, j is going to become 2n. So it's the sum from j equals 1 to 2n now of minus m to the 2n minus I. Well, I is j minus 1, so it's 2n minus j minus 1 times fn to the j of x, like so. Okay, let's just clean this up a bit. We can just essentially remove these brackets and then turn this into a plus, like so. Now what we can do is, well, we see that we've got a minus m to the power of plus 1, so let's just factor that out. So, like so. Okay, so we've got minus m times this sum here. Okay, well, have a look. This sum here looks kind of similar to what we have up here, except with the j replaced with I, but j and I are just dummy variables, so that's fine. Except here we're summing from 0 and here we're summing from 1. So perhaps let's add on the j equals 0 term and then subtract it again. But firstly, let me just divide through by this minus m. So here I'm going to have minus the nth derivative, the first derivative of fn of x divided by m, and minus that, equals this guy here. But what I'm going to do is just put from j equals 0 and then subtract off the 0th term from this guy here. What is the 0th term? Well, when I plug in 0 into this guy here, I get minus m to the 2n, which is just m to the 2n. And then that's times the 0th, so fn to the 0 of x, the 0th derivative of fn of x, which is just fn of x. Like so. Okay, so I get that minus fn prime of x over m is equal to this guy here minus m to the 2n times f of x, but this guy here is exactly this guy here, so fn of x. Okay, so this is precisely fn of x minus m to the 2n f of x, like so. Okay, let me bring this to the top of the whiteboard and we'll continue. Okay, so on the last whiteboard I introduced this function capital Fn of x, being this sort of linear combination of the derivatives of little fn of x. Okay, and we showed that minus fn prime of x over m equals fn of x minus m to the 2n times little fn of x. Now just rearranging this, we get fn prime of x plus m fn of x is equal to m to the 2n plus 1 f little n of x, or little f of nx. Okay, so we get this equation here, and you might be wondering why I've left these little gaps here, and that's because what I want to do is multiply through by e to the mx. Okay, so if you've seen first order differential equations before, where you solve using the integrating factor method, this will look a little bit familiar. E to the mx is kind of like our integrating factor on this left hand side. If you haven't seen that before, do not worry. We're just multiplying this equation here by e to the mx. So on this side we get e to the mx times the first derivative of fn of x plus e to the mx times m fn of x equals e to the mx times little m to the 2n plus 1 times little fn of x. Okay, and the key thing to notice now is this left hand side is an exact derivative. This guy here is precisely the first derivative of e to the mx fn of x. Okay, and to see that, just use the product rule. The derivative, if we differentiate this term and keep this term alone, leave this term alone, we get m e to the mx fn of x, which is this guy here. Then when we leave this term alone and just differentiate this guy, we get e to the mx times fn prime of x. Okay, so ddx equals, ddx of this term here gives you this guy here, which of course is just that right hand side, e to the mx times m to the 2n plus 1 times little fn of x. Okay, so we have this sort of identity here, which we're going to use in just a second. Now notice so far I haven't actually talked about rationality or irrationality, so that's what we want to do next. Let me clean up the whiteboard and we'll continue. Okay, so we just showed that the derivative of e to the mx times capital Fn of x equals m to the 2n plus 1 times e to the mx times little fn of x, and here's just the definition of capital Fn of x. Now what we want to do is suppose for contradiction e to the m is rational. Okay, so that means we can write e to the m as a quotient of two positive integers, let's say a and b. So we have that e to the m is equal to a over b, where a and b are positive integers, so natural numbers, like so. Okay, now what we want to do is introduce a quantity, namely a times fn of 0, fn of 1, sorry, minus b times fn of 0. And this might seem quite arbitrary, but hopefully once we see what it equals, it will make a bit of sense. But let's have a bit of a play with this. Let's firstly factor out the b. So this is equal to b times a over b, fn of 1, minus fn of 0, like so. But a over b is nothing but e to the m. So let me just replace this with e to the m. And we get this guy here. And hopefully this is sort of looking like when you're trying to integrate something, how you work it out. You get its antiderivative, then plug in the top limit, and then subtract the lower limit. So this is precisely b times e to the mx times fn of x between 0 and 1. Because obviously when we plug in x equals 1, we get e to the m times fn of 1, this first term here. And when we plug in x equals 0, we get e to the m times 0, which of course is just e to the 0, which is 1, times fn of 0, which is that term there. Okay, so this guy equals this guy. Well, what is this guy equal to? This is just b times the integral from 0 to 1 of, well, if we just go back up to this line here, we know that this guy is the antiderivative of this guy here. So we know then that basically, let me just write it out first. This is just this thing here. Okay, because obviously if we start from this line and we want to integrate it, well, we can find its antiderivative, which we know is this guy here, then plug in the top limit and the lower limit and gives us this thing here, and I'm just bringing the b across to here. Okay, so we've shown that this quantity here, a fn of 1 minus b fn of 0, is b times this integral here. Let me clean up the whiteboard, bring this to the top, and we'll continue, and we're almost done in showing that e to the m is irrational. Okay, so we just showed this identity here. A fn of 1 minus b fn of 0 is equal to b times the integral from 0 to 1 of m to the 2n plus 1 e to the mx times little fn of x dx. Now, if we look at this left-hand side, I claim that it's an integer. Now, to see that, recall that little fn and all its derivatives, when you plug in 0 or 1, are integers. That was one of the first things we proved. I think that was claim 2 that I had written on the whiteboard. And remember that capital Fn is just a linear combination of the derivatives of little fn, and in particular the coefficients of the little fn are integers. So when I plug in x equals 0, for example, capital Fn of 0, well, that's going to be equal to some integers multiplied by the derivatives of little fn of 0, and then you're summing them up. So you're summing up a bunch of integers times integers, so that of course is going to be an integer. So capital Fn of 0 is an integer, and for the exact same reason, capital Fn of 1 is an integer. Okay, so this guy's an integer, this guy's an integer, and remember a and b are integers, so we've got an integer times an integer, and an integer times an integer, and we're looking at their difference, so of course that's going to be an integer. So on the left-hand side we have an integer, but notice it equals the right-hand side, which is b, so something positive, times this integral here. But this integral is clearly going to be positive, because m to the 2n plus 1 is positive, e to the mx is positive, and fn of x is non-negative, and particularly it's not identically 0, and because of continuity and stuff, this integral is going to evaluate out to a positive number, but because we know it's an integer, in particular it must be a natural number, and in particular it must be at least 1. So the left-hand side equals the right-hand side, and both of them are at least 1, because we know it's positive and we know it's an integer, so it's 1, 2, 3, 4, something like that, but in particular it's at least 1. Okay, now what we're going to do is examine this right-hand side. Well, clearly it's non-negative. Okay, because each of the terms in the integral are non-negative. Okay, but what we can do is just apply an upper bound to this, because we know that, well, m to the 2n plus 1, that's just a constant, so in fact we can just take that out to the integral. But e to the mx, that's bounded in this interval 0,1 by e to the m, because obviously e to the mx is a monotonic increasing function, and thus in this interval it attains its maximum at x equals 1, and takes value e to the m, and we showed that fn of x is at most 1 over n factorial, so this guy here is less than or equal to b times m to the 2n plus 1 times e to the m times or divided by n factorial, and then I guess times the integral from 0 to 1 of dx. But of course the integral from 0 to 1 of dx is just 1. Okay, so we get that this integral here, which remember is this quantity here, which I'm claiming is at least 1, is bounded above by b times m to the 2n plus 1 times e to the m, all divided by n factorial. Now here b and e to the m are just constants, but notice we've got an m to the 2n plus 1 divided by n factorial. Now we haven't actually talked too much about n, but it's just some arbitrary positive integer, and we can choose it to be as big or as small as we want. And what we're going to do is choose it to be very, very big, and we're going to take the limit as n goes to infinity of sort of this inequality. So obviously this guy stays 0, and this guy, when you take n to infinity, you've got m to the 2n plus 1 divided by n factorial. The n factorial grows bigger, so this thing here tends to 0. So this guy here goes to 0, this guy here is 0, and because this is sandwiched in between, this guy here must also tend to 0. So in other words, we have that the limit as n goes to infinity of the integral from 0 to 1 of m to the 2n plus 1 times e to the mx times fn of x dx is equal to 0. But we've just showed this guy, or we said before that this guy here is always at least 1, and that's independent of what n is. So that would mean that its limit as n goes to infinity, should it exist, would be at least 1. But we've shown that the limit exists, but it's 0. So then that implies, I guess, that 0 is at least 1. And of course, that is a contradiction. We can't have 0 being bigger than or equal to 1. Because if that's true, then we have some bigger problems than the irrationality of E. Okay, but this is a kind of cool proof which doesn't use that too high level of maths. You don't have to, a lot of proofs to show the irrationality of e to the n, or e to the m, essentially just use the transcendental property of e to the m, but then that's kind of boring because that's kind of overkill, if anything, and to prove the transcendental property of e, that's a lot more high level. But to show that it's irrational, here's a really neat proof, which hopefully you may not have seen before, but if you have, hopefully it's a nice bit of revision and a nice, cool way to show that e to the m is irrational. Anyway, I'm going to stop waffling now. This has been kind of a long video. I'll catch you in the next one. Have a great day.